first talk is by Torge Jensen, and he will talk about induction of P cells and localization. So please, Torge, it's your turn.
Okay, well, thank you very much for the introduction. And of course, I also thank the organizers for giving me the opportunity to speak. It's been a very exciting conference so far. So, as Peter said, my topic will be induction of P cells and localization. And this is a little project that is joined with Leonardo Patimo from last year. And here's what I want to talk about. So first, I want to talk very briefly about localization techniques. And then after that, I want to mention the combinatorial problem. So induction of P cells. And in the third part, I want to introduce the Pika-Sandler-Stich basis, or sometimes also called P-canonical basis. And then in the fourth part, I'll mention a positivity property. Of the Pika-Sandler-Stich basis. And in the end, I'll explain how one can use these things to conclude and prove the result. And if time permits, I'll mention some conjectures, some open conjectures about P cells in the very end. Okay, so in the first part, I want to mention an important theme in geometric representation theory that if people have attended Jordi's talk last week, you'll be familiar with. So it's kind of this idea of having a group action on a variety. So if G acts on a variety X, then it's an important idea to kind of try to relate the information on the variety and on the with the fixed points. And as an example, you can think of an S1 action on X, and in this case, the Euler characteristic of the variety will actually coincide with the Euler characteristic of the fixed points under the S1 action, and this gives us a nice, very quick way to calculate, for example, the Euler characteristic of the two sphere, because we just have two fixed points, so the Euler characteristic of this is 2. So, I mean, you might have recognized this little example from Jordi's talk, which where I stole it from, basically. But this is not the setting we're going to work in. So Jordi was kind of interested in a GM action on the F1 Grassmannian or the F1 flag variety, and restricted this to this discrete circle kind of Z of the cyclic P group. But I want to go in a different direction. And so let me mention which setting I'm interested in. And so let me fix a simply connected algebraic group G together with a Borel B and a maximal torus T, all of this over C. And then in this setting, we have the Bruchau decomposition of the flag variety. If we denote by W the normalizer of the torus modulo of the torus, so the Weyl group associated to our pair GT. And we have this the Bruchau decomposition that we all know and love. And this is G mod B is kind of the disjoint union of the coset, the BW cosets BWB indexed over the Weyl group. Okay, so I mean, this is known to everybody in the audience. And so my favorite way to kind of like prove this is probably via the Bielaniki-Birula decomposition. And in this setting, what one uses is a GM action on G modulo B for co-character lambda. So lambda and xchach. So xchach will be the co-characters for me. And lambda, if we choose lambda dominant regular, you see that, I mean, first of all, it's like a well-known classical result that the that the fixed points will exactly be these WBs, the points BW in the flag variety. So I was a bit sloppy. I mean, in principle, maybe I should write this, I don't know. But so the point in the in the flag variety. And then for dominant regular, the Schubert cell BWB, so is exactly the attracting cell that when we take the limit for t equals goes to 0 of the action of lambda t on this on any point, this will exactly contract to this GM fixed point in the setting. Okay. So and now the question, well, this is also well known, but so what we are interested in today will be more the setting, what happens for lambda singular. And this is what I want to mention now. So I mean, I should say that all this is like very classical and it's nothing original. So in this setting, so if we take a lambda which is dominant and singular, and we can choose the stabilizer, let's say the stabilizer of our lambda in the Weyl group W is a standard parabolic Wi. So this is just my notation for the group generated by the subset I of the simple reflections, where S is a set of simple reflections generating W as a Coxeter group. Then to this setting, we can associate a parabolic subgroup P, and this comes with a Levy decomposition, L semi-direct product with U, and I hope this is not too confusing that I denote here in the setting U the unipotent radical of this parabolic and not of B, but yeah, I mean, we won't need this notation much. We basically just need L most of the time. And then one more piece of notation that we need is we need the minimal coset representatives, which I'll denote by I superscript W, so which are minimal in the left with respect to this smaller Weyl group. So all these elements in my Weyl group, which are minimal in their coset WIW. And then what one can see is, it's not so hard to check that actually, if one again considers the GM action on the flag variety G mod B under this dominant singular co-character, this time lambda, then one actually gets a disjoint union of smaller flag varieties, and these are exactly flag varieties that are isomorphic, the flag varieties for our little Levy factor L. And one has one copy of these factors exactly for any minimal coset representative. So we see that the fixed points are a disjoint union over Y and the minimal coset representatives LYB, where this LYB is isomorphic, as I said, to the smaller flag variety for L. And in order to see this, this is like one should notice that the stabilizer of the fixed point corresponding to Y in L is exactly this the standard Borel, as I mentioned here, the standard Borel in my Levy factor. So this is BL, and yeah. So this is and then using kind of that Y is minimal, you can kind of see that I mean, this is like using Y that Y is minimal, you can see that this is actually really the standard Borel here. Okay. And the second observation in this case, which is also not so hard to see, is that actually if you look at PYB, then this is the attracting cell for this fixed point component. So if you take, and in particular this morphism, the limiting morphism that sends a point in PYB to the limit where t goes to 0 under the action of lambda t on x again, that this is a topological bundle. And well, it's actually, I mean, you can see that it's L equivariant, and the fibers are affine spaces, yeah, of dimension given by the length of your element Y. Okay. Are there any questions about this? I think this is like very classical, and I hope most people know this. But this is exactly the case we're interested in. So let's look at a quick little example. And so in the example for SL3, we have that the Weyl group is our symmetric group on 3 letters, and the set of simple reflections will be will be S and T, denoted by S and T for me. And so if we choose lambda and XCH dominant with stabilizer of lambda, the subgroup generated by S, for example, then we'll see that kind of in the Bruja graph, which encodes, which is kind of just a concise way of encoding the T fixed points and the one-dimensional T orbits between them, we see that that our flag variety for SL3 is glued up out of 3 bundles over the flag variety for I mean in this like over P1s basically. We have basically 3 bundles, like, and the first one is just a P1, the second one will be a bundle with fiber dimension, with fibers of dimension 1, and the last one, this piece here, will be a bundle here of with fibers affine spaces of dimension 2. So if there are no more no questions about this, then I'll move on to the second part. And in the second part, I want to talk about the induction of P-cells. And so in particular, this is kind of the question, which combinatorial problem are we trying to solve? And so in order to explain this, I need to introduce the Hecker algebra. And so you'll notice that I'll work in a more general setting here. So if WS is a crystallographic Coxeter system, then to this I can associate the Hecker algebra, which I'll denote by H subscript WS. And this is a deformation of the integral group ring. So we get we view this as an algebra of a Laurent polynomials in one variable, so ZVV inverse, and the standard basis will be denoted by HW. And these satisfy the following relations. So HX and HY multiplied to give you HXY if the lengths add up to give you the length of the product. And we introduce this quadratic relation where you see if you specialize V to 1, you get back your integral group ring, so that HS squared equals V minus V inverse HS plus the identity. Okay, and the fact, an important fact, which I'll come back to later, as I said, I'll talk about the Picasso and Lustig basis in the third part, is that this Hecker algebra has a p-canonical Picasso and Lustig basis, which I'll denote by PH underline W for W and W. So it's still indexed by the elements of our crystallographic Coxeter group. Okay. And now a very important fact in this setting is that for p equals 0, the p-canonical basis actually coincides with the Castan-Lustig basis. So I mean, I'm not 100% sure who I should attribute this result to in the setting, but I mean, I put here Castan and Lustig because they actually originally in their first paper, and one of the first papers, show that the Castan-Lustig basis is related to IC sheaves. And then I guess Herterich in his PhD thesis kind of generalized things to the setting that we're actually working in. But you'll see this in the next section, hopefully. Okay. And then motivated by this, there is a very straightforward generalization of Castan-Lustig cells. So we first introduce the P-cell preorder, saying that X is right P smaller or equal than Y, if and only if this Castan-Lustig basis element corresponding to X occurs with a non-trivial coefficient when we express a product of PH underline Y with an element of any element of the Hecker algebra H on the right. Okay, and it occurs in this expansion, the p-canonical basis. And then the definition is that the right p cells are the equivalence classes with respect to this pre-order. Okay, and then the original motivation to introduce Kastner-Lustig cells was to explicitly construct representations for the Hecke algebra. And so I'll quickly explain how this works. So this is a very easy construction. So if we take a cell C in our W, so the equivalence, the right cells or the cells are just subsets of the index set of our bases. So they will be subsets of our group W. And to this, we can associate a cell module by just taking the span of all the Kastner-Lustig basis elements that are right smaller or equal than an element, an arbitrary element in C. This is what I'll denote by this notation here. So this will be a right module, and then we'll quotient out by the span of all the P-Kastner-Lustig basis elements that are strictly smaller. So they're not actually in C, but they're smaller smaller than an element in C. Okay, and this gives us the right module for our Hecke algebra. Okay, and the question that I want to mention today or talk about today is the question of induction of P cells. So if we have a finitary subset, so I'd fix a subset I in my set of simple reflections, and finitary just means that the corresponding standard parabolic subgroup is finite, and we fix a cell in the smaller Wahl group. And the question is, I mean, it's a very natural question to ask. We can induce this module up to the big to the big Hecke algebra, and the question is, does this decompose into cell modules? Are there any questions about this before I move on to the third part?
Maybe, can we have maybe just one example of W and of P where a right P cell is smaller than the right Kastner-Lustig cell? I mean, just you don't have to write it. Just to if you could remind me, I forgot. You.
So sorry, yeah. So the first example already occurs for B2 for P equals 2. And so in dihedral groups, one can, what one usually sees is one has the identity element as a cell, the longest element, and then what Lustig calls strings. So one for the right cells, one fixes the left descent set and one gets 2 strings. And in B2, we see that one of the 2 strings splits up and the simple reflection forms a cell on its own, and the other 2 elements give another P cell. So this is like the simplest example where the P cells differ from the Kastner-Lustig cells, but it just happens for one of the 2 strings.
Okay, thanks. So it's beautiful. It shows also the difference between B2 and C2 there. Okay, back to
yeah, exactly. So
yeah,
this example shows already that the P cells really depend on. I mean, they see more than the Kastner-Lustig cells. Yeah.
Yeah. Okay. Thanks.
Any other questions before I move on? Okay, so then let me mention explain where the P-canonical or P-Kastner-Lustig basis comes from. So in this setting, in order to kind of match the generality of the second part, I want to use a generalized Cartan matrix as input, and to this one can associate a Kac-Moody root datum. So and eventually also a Kac-Moody group G with a Borel subgroup B. And so in principle, one can construct this as an int group scheme in like very large generality, but we only need the complex points. So for us, the construction of Kummer will be enough. And we'll consider in the setting like a Kac-Moody flag variety, which has still an affine paving. So it still has, I mean, also to this generalized Cartan matrix, you can also associate a crystallographic Coxeter group. I mean, I don't want to go into too much detail here, but and then the elements of the group will still index our Bruchhaus cells in the setting, and the Bruchhaus cells will all be affine spaces. of dimension given by the length of the element. And then we'll fix an algebraically closed field of characteristic P, which is greater than 0. And we're going to consider the B equivalent bounded constructible derived category following Bernstein and Lunds on this Kac-Moody flag variety. So again, of course, this is like an infinite variety. And I mean, depending on our input, but it may be infinite dimensional. But all the sheaves are like we're considering will be supported on a finite union of these Bruchhaus cells. So yeah, this shouldn't be a problem. And then what we're really interested in is the full subcategory of parity complexes, which I'll denote by parity subscript B, G mod B, comma K. So these are complexes of sheaves on this Kac-Moody flag variety with coefficients in my field K, such that whenever I restrict them to one of our, so we have this Kac-Moody flag variety, which is stratified by the Bruchhaus cells. Whenever we restrict one of these complexes to one of the strata, we want the sheaves to satisfy cohomology, like that the odd cohomology vanishes. Okay. And now I want to mention a couple of properties of this category. And so the first property that is very nice is that it's actually a Kohl-Schmidt category. So that means that any object decomposes as a finite direct sum of indecomposable objects in this category. And then this means that if you want to understand or get a basis of the, for example, additive of the split Grothendieck group of this category, it's enough to understand the indecomposable objects. And what is also very nice about this is that the indecomposable objects, they have a classification similar to the classification of perverse sheaves, or I mean, similar to the simple perverse sheaves, the IC sheaves. So in principle, it means that we have one self-dual indecomposable object, which I'll denote by this this letter, this mathcal EW per stratum. And again, I mean, here plays, of course, a role that our strata are simply connected. So they just have one, I mean, they just have to afford the trivial local system. Okay. And another thing I want to mention about this, another fact that will be important for us is that this category actually gives us a geometric incarnation and positive characteristic of our Hecke algebra, HWS. And this is by, I mean, the classical construction that one does. I mean, in principle, one can pass to the Hecke algebra by kind of taking dimensions of stalks. And I mean, the explicit formula is not important. And when one passes to the split Grothendieck group, this will induce an isomorphism between the split Grothendieck group and the Hecke algebra. And so the split Grothendieck group, this is just a group where we only quotient by the relation that the class of the direct sum is the sum of the classes. And then the image of the self-dual indecomposable object, this will give us precisely the p-canonical basis or p-Kastianistic basis element pH underline W. And basically from these two properties above, we see immediately that this gives us the basis of our Hecke algebra. Are there any questions about this? Before I continue with the next part. Okay. So then I want to mention a new positivity property of this p-Kastianistic basis. And this positivity property will be with respect to what we call the I-hybrid basis. I mean, some people also call it mixed basis, but somehow mixed is a term that's already widely used in many settings. So we try to avoid this. So what is the I-hybrid basis? And so this is just a combination, kind of something that interpolates between somehow the standard basis and the p-Kastianistic basis of our Hecke algebra. So remember that I denoted by this I superscript W, the minimal coset representatives for cosets on the left. And so we can write any element in our crystallographic Coxeter system uniquely as a product of an element in my smaller Weyl group and a minimal coset representative. And using this, we can kind of combine these two bases to get a new basis, which we call the I-hybrid basis of the Hacker algebra. And so we'll take on the small Weyl group, we'll take the p-canonical basis, and then we'll kind of move this up by taking the standard, multiplying by the standard basis element corresponding to this minimal coset representative. And by looking at the base change matrix, you see that this will be upper triangular in a upper triangular, and you like deduce immediately that this is a basis. So this is not so hard to see. And now I want to explain in this section why the p-canonical basis element, kind of coming back to this very first setting where we saw that our Kac-Moody flag variety is kind of glued together out of bundles over the smaller flag variety, how one can use this to kind of see that the p-canonical basis element is positive with respect to this I-hybrid basis. And for this, I want to consider the following maps. So if we fix Y minimal coset representative, we can look at the inclusion of our attracting cell PYB into our Kac-Moody flag variety. Then we have our attracting morphism PY, which is just the limit, just to recall you, the limit kind of for t equals goes to 0 of the action of this singular co-character, singular dominant. And then we have an isomorphism, as I mentioned previously, between this fixed point component and the smaller flag variety for our Levy factor. Okay, and then it's an important observation that actually kind of pulling back along the inclusion and pushing forward along the attracting morphism and kind of pulling back along the iso, that this preserves parity complexes. And the crucial input into this is that this functor is one component of Braden's hyperbolic localization functor. And Daniel Juteau, Karl Mortner, and Jody Williamson have already proved in a paper where they studied the relation between parity sheaves on the affine Grassmannian and and basically the compatibility or the images of these under the geometric Satake, that Braden's hyperbolic localization functor preserves parity sheaves. Okay, so this is then using this follows immediately. And then the only thing that that one needs to kind of observe is that the coefficient basically of when we take a sheaf on the Kac-Moody flag variety, well, I should have B equivalent here. So that whenever I want to express, if I want to express the character of this sheaf in terms of this I-hybrid basis, the coefficient in front of PHX underline HY is precisely the coefficient of V to the L of lambda times the coefficient of the peak of the character of basically this functor that preserves parity sheaves applied to this complex F, the coefficient of this expressed in the p-canonical basis. And so in order to see this, basically we see that by the previous proposition that that this term here is a parity complex. So when we express its character, this will just give us a non-negative linear combination of the p-canonical basis. And then this coefficient here basically just comes from the fiber dimension of our affine bundle along which we kind of push. So this one sees by kind of push-pull arguments. And then as a consequence, we see, as an easy consequence of this, we see that when we express the p-canonical basis element corresponding to X in the I-hybrid basis, the base change coefficients will be Laurent polynomials with non-negative coefficients. And this is, this was, probably known to the experts, but this is kind of the geometric ingredient to this induction property. Are there any questions about this before I move on to the next part? And Okay. And then kind of in order to use this to conclude, this is in the last part kind of, I want to just sketch the last two ingredients in order to kind of deduce the main result from this. And this follows ideas of GAC. And it's very interesting and kind of skillful combination of Bruja and P-cell structures using this hybrid basis. And so the interesting property is that basically GAC combines, I mean, he proves this for Hacker algebras with unequal parameters, the induction property. So he doesn't have positivity, but he kind of, has other properties instead. And so what one does is one combines the Bruja and the P-cell pre-order to get what we call the I-hybrid order. So this is very, I mean, natural in the setting. So if I take two elements X and U in the smaller Weyl group and two minimal coset representatives Y and W, then I say that XY will be smaller in the I-hybrid order, the PI, well, than UW, if and only if basically X is smaller or equal than U in the in the right P-cell pre-order, and Y will be smaller than W in the Bruja order. Okay, and then the most important observation that one can prove is that still when we express the p-canonical basis in terms of the I-hybrid basis, that the coefficients, that the base change matrix will be upper triangular in a total order, refining this I-hybrid order, I-hybrid order. Okay, so this is precisely what this next proposition tells us. So we see that the p-canonical basis element corresponding to xy, we have exactly once the I-hybrid element ph underline x hy occurring, and then all the other terms will be smaller in this I-hybrid order. Okay, and in this case, we use this crucially kind of this positivity property, and GAC uses the characterization of the Kassan-Lustig basis as the minimal self-dual element, which is no longer true in our setting. Okay, and then from this, one can get the following theorem, and this is actually a reformulation of the induction of P-cells property that I mentioned earlier. So this says precisely that if we have two elements in our smaller Weyl group, X and U, and two minimal coset representatives, Y and W, that UW will be smaller or equal than XY in the right P-cell pre-order in W, then this implies that actually the elements in our smaller Weyl group will already be smaller in the P-cell pre-order in the small Weyl group. Okay, and in particular, so that means if they lie in the same cell, then of course the the elements will also lie in the same cell in Wi. So from this, you can see that if you take a cell in my smaller Weyl group, a right cell, and I multiply it with basically the set of all the minimal coset representatives on the right, this will be kind of an index set for this induced module that this decomposes into into right cells for the larger group. This is more or less immediate from this. So let me mention a few historical remarks. And so this was originally proved by Barbash and Vogan in '83 and Lustig in '84 for Kassan-Lustig cells in finite Weyl groups. So this uses kind of connections to primitive ideals and the classical theory. And then it was conjectured by Reuchmann in '98 for Kassan-Lustig cells in arbitrary Coxeter groups. And GAC proved it in 2003 for Hacker algebras with unequal parameters. Okay, and then I want to mention some further remark about this is that basically it's a very natural hope that the p-Kassan-Lustig cells in general, or that the Kassan-Lustig cells in general decompose into p-Kassan-Lustig cells. And unfortunately, this is not the case. So I found a little counterexample in finite type C3 for p equals 2. But what is interesting is that this result already allows us to kind of predict this non-trivial decomposition behavior. So in finite type C3, what one sees is one has a union of two Castle-Lustig cells, which decompose actually in 3p cells. Are there any questions about this before I kind of move on to the last part?
Can you just repeat the last thing? So the last statement is some. I didn't hear the parabolic part. You have two Kazhdan-Lustig cells decomposing into 3p Kazhdan-Lustig cells.
Yeah, so I have two in finite type C3 for p equals 2. I have two Kazhdan-Lustig cells, which like the union of two Kazhdan-Lustig cells, which decomposes non-trivial into 3p cells. So
okay, thanks.
Yeah, so basically one lies
Okay.
kind of and contains parts of both Kazhdan-Lustig cells.
And also, you mentioned about some earlier work along this line. And is this in any way related to Dioda's work on parabolic canonical settings of Kazhdan-Lustig polynomials, where he also takes a Levy subgroup or take a subset I?
Whose work? That? Sorry, I didn't.
Vinny Dioda.
I'm not aware of this, so I don't know if it's related or not. I'm sorry.
Yeah.
Maybe we can discuss.
We'll discuss after.
Okay. And I want to mention another parabolic compatibility result, which I proved during my PhD thesis, and this is kind of the restriction result. And so basically, if we take a right p cell in the bigger group, and this time I need the minimal coset representatives for the cosets on the right, then we can ask if we take the p cell module for the right cell in the bigger cell in the bigger crystallographic Coxeter group and restrict it to the small group, does this decompose into cells and into cell modules? And I give an affirmative answer for this. Which is relatively simple, as you can see here. So it decomposes a direct sum of all these cell modules where I take a right cell in the small group and a minimal right coset representative, and basically all the cells where the product of the minimal coset representative and the cell is contained in our bigger cell. Okay, are there any questions about this? Otherwise, I'll mention a couple of, in the last, 2 minutes that I have left, I want to mention a couple of open conjectures for P cells. And so the first one is related to the following setting. So if one has a finite value group with the longest element W0 and one takes a right P cell in W, then in all the examples where I can calculate the P cells, we can see that the standard basis element corresponding to the longest element acts on this cell module by permutation up to a sign and the power of V. And this is known in characteristic 0 by work of Matas, Lustig, and also, well, you can, a couple of people have worked on this. And well, this is somehow related to what some people know to kind of a cactus group action. And the hope is, or this should be somewhat related to some perverse equivalence in the background, but yeah, unfortunately, this is still open. So this is something interesting to think about. And then another conjecture, which is due to Paramat-Achar, William. Oh, thank you for Ben for the Graham Lara in type A. Okay, I guess there was an earlier reference than Mathas. And another conjecture I want to mention is due to Paramat-Achar, William Hardesty, and Simon Risch. And this is kind of related to this question of decomposing Kazhdan-Lustig cells into P cells. And I'll need to explain a little bit more where this comes from. So basically, in Kazhdan-Lustig cell theory, one can define what an antispherical right Kazhdan-Lustig cell is. So these are these are precisely, so if here FW are the minimal coset representatives. So here we're working in the setting of an extended affine Weyl group. And these are the minimal coset representatives for the finite Weyl group on the left. And so what Lustig and he show is that there any two-sided Castaner-Lustig cell intersects this set of minimal coset representatives FW in a unique right Castaner-Lustig cell, and they call them canonical. But I somewhat prefer the notion antispherical as introduced by Achar, Hardesty, and Drisch. And moreover, Lustig shows that there is a one-to-one bijection between the two-sided Castaner-Lustig cell. This is like the deepest result in Castaner-Lustig cell theory, and the nilpotent orbits in the Langlands dual group. And so combining all these bijections, we can associate to a Castaner-Lustig right cell C a nilpotent orbit in the Langlands dual Lie algebra, OC. And then what they conjecture is that for p greater or equal than the Coxeter number, they conjecture that the decomposition of this antispherical Castaner-Lustig cell C into right p cells is governed actually by the reductive quotient of the stabilizer of a point in OC. And this is motivated very much by this beautiful fractal-like behavior that one sees for p Castaner-Lustig cells in affine Weyl groups that you may have seen in my postdoc short talk about p cells. And this is just kind of, this phenomenon kind of comes from, would be the special case where under this bijection, the lowest or the lowest antispherical right Castaner-Lustig cell corresponds to the zero nilpotent orbit, whose stabilizer would then be kind of the group itself. And so this group itself, or I mean a Frobenius twist or something, but I mean the group itself, and this this would govern kind of again the decomposition behavior of this cell and predict somehow this like fractal-like behavior that one sees. Okay, and then the last, because I'm already a bit over time, the last conjecture I want to mention is a conjecture just very briefly about the existence of p-distinguished involutions. And so if one has a crystallographic Coxeter group and a right p cell C, well maybe maybe I should restrict to finite or affine Weyl groups, but and then my conjecture is that the C contains a unique involution D that can also be numerically identified, and this I want to call a p-distinguished involution. And so in the setting, I mean, the numerical characterization that I can see in all the examples where I can calculate this is that the degree of the structure coefficient mu dd, so where I basically look at the coefficient or the multiplicity of the indecomposable corresponding to D in the tensor product of the indecomposable with itself, that the degree of this, so the highest grading shift occurring in there, is greater or equal than the valuation of a certain p Castaner-Lustig polynomial at the identity. And in the Castaner-Lustig setting, Lustig has, I mean, the distinguished involutions are known to exist, and they satisfy, they're exactly, one has in general an equality for Castaner-Lustig for p equals 0. So let me put this in green maybe. So this one has in general this kind of equality, and the distinguished involutions are characterized by equality according to results by Lustig. And so in the p Castaner-Lustig setting, one can see that elements can really violate this inequality that one has for Castaner-Lustig settings, for Castaner-Lustig cell elements, basis elements. So thank you very much. I think this is all I wanted to mention, and now I'm happy to answer your questions.
Well, thank you very much, Torge, for your beautiful talk. We have time for questions.
Can I ask, so about cactus type actions, are there things that are already constructed, or are there certain things that are conjectured to work?
Yeah, I mean, this is in principle, like in all the cases where I can really calculate this, I can see that this longer element acts by kind of this permutation up to a sign in the global power of V, but like currently we don't have a way to really, I mean, I don't really have a good approach to this. I mean, in principle, it would be very nice if one had kind of a modular version of this equivalence of the two realizations of the Hacker algebra proposed by Roman Bezrukovnikov, but this is not yet available. So potentially one can hope to use kind of things like this to deduce this.
Is there a bread group action? Can you realize a bread group with a mod P Hacker category with, or when if you take your parity sheaves and take I don't know, complexes, homotopy category of complexes of parity sheaves, do you still get the bread group or not?
Yeah.
So you could try to do what you're saying, the perverse, use this perverse equivalences, do what Ivan Lozev had done, and check. So there's a question of whether or not, checking that it's perverse. But once you know it's perverse, then you can at least that will define something. It's a question. It's going to be some permutation. The question is whether you can compute it.
But even coming back to Ben's comment, I think, is this like completely clear that you even have, I mean, have the braid group and positive characteristic? I mean, this is definitely not anywhere in the literature, right?
You mean that it's a faithful action?
Yeah, that's yeah. Well, no, that
not
it's kind of faithful categorification of the braid group, like in this setting.
You don't need faithful. You just need I mean, you just want to have operators for each simple reflection to get started with this Lozev cactus action.
But so there's a sort of a stronger conjecture than, or maybe equivalent, but which is that the full twist is categorically diagonalizable in on P cells. I
mean, yeah, I'm asking for less. I'm just asking for not just W's. I'm not asking about W0, but somehow for already for individual, you see, simple reflection, just to get started. I understand that you're asking, you're already going directly to the hardest somehow, saying something. Then you want to do it for longest elements of parabolics. And typically there's a W0, and then you can have this, you're saying you have this precise conjecture about diagonalization, but there is already, you want to start with rank 1, and then if it works, look at parabolics. So you expect the W0 to have the same property as in characteristic 0, otherwise, okay.
Yeah, so Ben and I did some calculations, I mean, in like rank 2, and it looks like that the diagonalization things still go through, but all the techniques from their paper in positive characteristic kind of break down, because you don't even have I mean, you don't have perversity of the Ruckier complexes anymore and things like this, so it gets...
Oh, wait, it's not perverse anymore. That was somehow...
No, that's exactly the point. The lack of perversity is what picks up the P cells.
Wait, and what about simple reflections?
For simple reflections, everything's fine.
So it's perverse, but it's, as soon as you have a longest element of a parabolic, it needs not be like the longest element of longest element in type B2.
Yes,
in type B2 is not perverse.
You don't need a long.
Perverse.
No, I mean, so not perverse in the sense like not diagonal, like I mean, where you play out the grading, homological and the grading shifts. But I mean, it's a bit a question of like, you can still generalize this like perverse T structure, and the things will still be, I mean, in the heart of this, I think, but it's not perverse in the diagonal setting idea. So
it's not perverse in the sense that you have this order on the indecomposable parity sheaves, so that by applying W0 you get another one modulo smaller ones. It's not true. You don't have triangularity. Like I mean, we have this definition of perverse with Zhou Shuang. It's not perverse in that sense.
This I haven't.
So you're taking one of your indecomposable thing. At home you call it BW. You apply your W0 thing. So you multiply, say, by TW0, and you have this result. Is it due to Lustig, or I forget what due to? That tells you that it's a new cache diagnostic element. You'll have with a permutation another W prime, or you'll have this indecomposable circle thing. And then there will be other terms, but this other term would be corresponding to smaller elements in the val group. So is that still true or not true? That's true.
So this is like what the conjecture is about. So
Okay.
I can see this
Okay,
in all the
perfect.
examples, but
Okay, that's what you're saying. Okay. Okay.
And not just in lower cells, also in lower homological degree.
Okay, so exactly like in the whatever Lustig,
Right.
maybe Lustig Gecko or whatever it is, Lustig Matas.
Yeah.
yeah, exactly.
And
Yeah.
Lustig Matas.
Inherent,
So
okay.
you're conjecturing that Lustig Matas is at the level of Hecke algebra. It's decategorified. So you're conjecturing that Lustig Matas formula holds for P cache diagnostic basis element times TW0.
Yes, but well, I mean, the permutation might be different. So we see
Sure, but,
cases where
yeah.
kind of, yeah, I mean, but in principle, like in an analog of this, like formula holds. Yes, this is what I conjecture.
But for type B2, for example, it would be the same permutation, isn't it? Because in your cells, right cells with 3 elements, the
Well,
simple reflections are fixed.
This is its own Schutzenberger dual now. Didn't used to be.
Yeah. So I don't remember, but I think kind of like in B2 it would flip usually the strings.
Yeah, normally, yeah, this thing gets flipped.
And now kind of it gets trivialized somehow, the permutation on the other string that splits.
Yeah, and this is a
trivial
new
on
involution, a new distinguished involution.
So involution of this length 3 cache diagnostic right cell splits as a disjunct union of naivos R2, a singleton and a pair, and even on the pair, it does not act on the pair, or it does
No,
act.
it's trivial on the pair, I think. Yeah.
Okay. Whereas in the normal cache diagnostic theory, it does act on the pair. Correct? It switches them on the pair. Okay. Okay. Thanks. Okay. That's incredible. Okay. Thank you.
Okay.
And one other thing to point out is that normally, like normally associated to a cell, you have two numbers, the A function and the A function of the transposed partition, if you will.
Yep, small a and big A, yes?
Yes, that's right. And so for P cells, sort of small a agrees with the normal cell, right? But the big A is weird and some new thing.
Yeah, I mean, it makes sense because the small a and big A have to do with kind of Frobenius. One is to do with the weight structure. Some of the combination has to do with having both the homological and the weight parameters. And now you have only one parameter. You don't have this separate. Is that correct? This separate. Oh no, you still have two parameters, but they are not. One is not a true geometric weight. So that's maybe why.
So can I ask a question also?
Sure, yeah.
So how about I think for P equals 0, if you take a left cell, you multiply by W0, you get another left cell. Is that true in your case in this P?
So unfortunately, this is not true any longer.
It's not true. Okay.
So which I find very confusing as well. So I don't know. Like this is why also, I mean, the combinatorial proofs already. I mean, it's clear that none of this like goes through in any setting. So like, yeah, in D4 you see cases also where you kind of you don't obtain a cell anymore by multiplying with.
Okay. Yeah. And the second question: is there analog of J-ring? This asymptotic algebra for this?
So that's a very interesting question, which I thought about a little bit with Maki as well. And like the first step would already be to kind of find a good analog of the A function that you defined for the P cells. And I mean, there's a naive generalization using the multiplication of the P canonical basis, but there are many other candidates. And the problem is the naive generalization doesn't satisfy the properties that it's constant on two-sided P cells, and so there are many kind of defects and many things going wrong. It seems like currently it's not at all clear how to define a J-ring.
Okay.
But I mean, the hope is that potentially if one finds a very good or a nicer definition of a function, then maybe one can still do this. I don't know.
But
Another candidate one could use for the a function would, for example, be something like a Frobenius-Perron dimension of the corresponding cell module, which still seems to behave very nicely. But even that, I mean, I haven't checked all the details. There's still like, yeah, I still need to kind of think about how you get monotonicity with respect to the cell order.
But your last conjecture in this talk was something in that direction, I think, because you are defining the unit element of the J ring somehow, no?
Well, I mean, in characteristic 0, they're related to the unit element. But I mean, that would be then the next question, if these p-distinguished involutions that one gets, if they're the, I mean, if they're they give something related to the unit element. So even in situations where we see that kind of, for example, in type B2, we see that new p-distinguished involutions occur, but the A function still is constant on two-sided P cells. So one could just consider the classical J ring as defined by U. In this setting, we see that, since we kind of change, we add new p-distinguished involutions, they don't add up to the identity anymore. I mean, we kind of have kind of like the simple reflection that splits off. All of a sudden, this occurs kind of like twice in there, and so this messes you up. But yeah, I mean, I don't know. I mean, there's definitely something interesting to think about.
There's a homological approach to the J ring, which isn't really worked out yet, but is more likely to work. Where instead of just truncating to the bottom piece, you sort of kill all the higher summands with more parts of some differential, and that's more likely to work.
Okay.
That's basically the categorical diagonalization way of doing things. So.
Okay.
But the J ring will not have, for affine bar group, it will not have unit element because there will be infinitely many left cells, I think, if you understand. Is that right?
So yeah, this is another thing that you have. I mean, you show that you have finitely many two-sided cells, and in the affine Weyl group, you have infinitely many two-sided cells already. Yeah. So this is definitely, yeah, I agree. I mean, but kind of for subrings, one could kind of have.
But a fixed two-sided cell, can it have infinitely many left cells?
Well, so a fixed two-sided cell, this is like we don't see yet. Like I'm not sure. I hope not, but I'm not sure. I mean, then things would get pretty bad if this was the case. But yeah, I don't know.
Okay, are there any more questions for Torge?
Well, if there are no more questions, then I maybe want to say one last thing that I forgot to mention.
Sure.
This is kind of like independent work, but I just wanted to mention this still. Like, unfortunately, some people have already left. But so the thing is that kind of during my PhD, I developed some like more powerful algorithms to calculate the P-going basis of the anticircle module. And this kind of, when I studied the combinatorics of the Smith-Truman localization of the anticircle module, then I realized that actually the new calculations give a counterexample to Lustig-Williamson conjecture on second generation tilting modules for SL3. So this Billiard's conjecture that some of you may know. And so, but I have kind of like a proposed correction for this. So if you're interested in either kind of the counterexample and the correction or the combinatorics of the Smith-Truman localization of the anticircle module, then please contact me, and I'm happy to explain this in more detail.
So how long did the computer calculate to find the counterexample?
So, I mean, I think Jordi originally wrote that for the paper, the calculations took like 10 months. but like getting to that point, we can do now in less than like in 16 hours or something. So it's definitely a huge improvement. But like, let's say after a month, I mean, we can calculate some more things, but the problems currently for the calculations is that in these intersection forms that occur, which are in principle like integral matrices, we have terms that have like hundreds of millions of digits. And it just gets incredibly difficult to work with this. And somehow we don't see a theoretical reason why this should occur. So we've tried a couple of things, but we haven't, I don't know. I mean, yeah, maybe this is still not the right way to approach this. I mean, who knows?
Okay, so anyone interested in this project, write an email to Tage. Okay, well, thanks again for this very nice talk.